instrumentation at Durham University. He's a great expert in RTC design, and he will be introducing today to the Adaptive Optics real-time controller, which is the RTC that has been developed for Harmony, and also is the one that will be used at EST. So good luck, David.
Yeah, hello everyone, and thank you very much for having me and having me come out for a few days. It's been a lot of fun so far. So yeah, as Nico said, my name is David Barr, and yeah, I work at Durham University. So I know you guys have worked with Durham University in the past, and you probably know of a guy called Ali Basden who worked there many years ago. Anyway, he left us for running supercomputers. And so I was hired kind of as his replacement to take over leading the real-time control work in Durham University. So yeah, as Nico said, I'll be talking to you today mainly about the new real-time control system we're developing called DAO. And so I'll give you a very brief overview of the history of DAO so far, what DAO is, how it works, and where we are going in the future. So very quickly, myself and a guy called Sylvain Set were hired by Durham University in 2022 to take over the real-time development work for Harmony. This was after Ali Basden left. And so we didn't plan to build a generic real-time system that it was going to be used in labs around the world. We were hired on to build one RTC for Harmony and one RTC for Mosaic, two ELT instruments. So yeah, so we took that and we were really aiming to build one system, not many. And so we decided, myself and Sylvain, to sit down, discuss what we liked about systems we've used, what we didn't like, and really the goal wasn't ever to build the best performing system ever. 10, 15 years ago, when I joined the field, when the ELTs were in their very early design phase, the questions we were asking were, can it be done? Is it possible with commercial technologies? In the last 10, 15 years, that question now has changed to, yes, it can be done. How's the best way to do it? So we really took that and focused on how the best way to do it, not can it be done. So we were very inspired by the work that Olivier Guyon was doing over in Gemini, Suru, and he developed a library called ImageStream.io that uses shared memory to pass data between objects. And so we decided that we wanted to baseline our work on this idea of shared memory. And unfortunately, we wanted very early to be involved in his stuff, and we all work together. Unfortunately, for the lifetimes and just lifespans of ELT instruments compared to test beds, you really need to own your code. So we took that, built our own system, but we are dedicated to remaining compatible. It's just in the future, if our paths differ, we can maintain our own code base. But the idea is we're in very good contact with that team, and we're trying to keep them the basis of the RTC aligned. So yeah, it's based on, so Sylvain worked at Keck, running their RTCs. Before I joined before I joined Durham University, I worked at ESO, and I was maintaining their Sparta system and doing some risk management on the ELT. So our goal in creating a new one was really take the best bits of what we've seen and make it simple to use, so that it was really get the hard part of the RTC away from AO scientists so they can focus on doing what they do best, which is AO, not trying to get pixels from a camera or move an actuator. So that's really been our goal all the way on, make it simple for the user and hide all the complexities. And so, yeah, we've already developed bits of this. We've got telemetry systems, logging systems. We use GPUs, CPUs, no matter what. And so far, it's all been Unix, but we're moving away from that at the moment to support pretty much any system, any operating system you want. So what do I mean by shared memory? This is really at the heart of everything. In the RTC, we don't want one monolithic block. So you just don't press go and one process launches and it controls your cameras, controls your DMs. That becomes very, very hard to manage in terms of modifications or future expandability. We want to decompose our entire system down into logical blocks. And so that you have one process doing one thing and it does that one thing brilliantly. So we have one process that writes some data into a shared memory. This is mapping a file system into RAM that we can access from two programs. We have some synchronizations. In the header, we can write things like frame ID, counters, timestamps, other metadata that might be useful. We got the payload where all the useful information of what's being written. So this may be pixels, it may be slopes, it may be DM commands, whatever you really want. And so really the idea of this is to allow two processes to share some memory, so you can part as an interface between many different processes. So I'm going to skip forward quickly. So if you take this as a very, very standard adaptive optics real-time control pipeline, we've got camera readout, calibration, wavefront processing, wavefront reconstruction, some control filtering, combining and sending your command. We want to interject the shared memory between all of the different processes, and that's the interface between them. So your calibrator is one process that on one side looks at pixels, raw pixels, on the other side will look at calibrated pixels. That's all it does. It doesn't care what your wavefront reconstructor is doing. It doesn't care what the DM commander is doing. It just sees two files, one that is your raw pixel, one that's calibrated pixel, and it just works on those over and over again. Doesn't care about anything else. Super simple to write, super simple to manage, and just really takes away a lot of the big complexities of the system. So going back, yeah, so all the processes are completely independent. All the data is, so those formatted shared memories are the same everywhere. The payload may be different, but the structure is the same. So you can be accessed by many different programs. The synchronization is extendable, so you can have many processes looking at the same shared memory. So that means that comes really useful if you want to attach monitoring scripts to see what's going on and monitor your pipeline. So they're easy to synchronize because we've got synchronization built in. We can distribute these across machines. Yeah, it's the biggest advantage, it's flexible. It's very, very quick for me to get a PhD student in the lab to kill one of my processes, write their own in Python in half an hour, have it running. It may not run quickly, but it will run. And honestly, on a lab bench, that is incredibly powerful, that you can get PhD students writing their own implementations quickly, test them before we spend time and energy and money optimizing them for use on telescopes, or even just optimizing them just to get it running at full speed. So the other powerful thing is it really decouples hardware from software. So all your hardware talks to one process and writes in shared memory. Nothing else needs to worry about that interface to the hardware. So if you kill a camera and you replace it, you replace one piece of code, not the entire pipeline. So it becomes very easy to change out hardware very quickly. Anyway, the code doesn't care if hardware's there. If you have the pixel calibrator, it doesn't care if a camera is writing into the shared memory. It could be a Python script that takes FITS files and writes into shared memory. The same code works on everything, so that we can really numerically test this without full systems. So every process is independent. So yeah, as I was saying, you could inject data you've got a Python test script, it injects data in a shared memory. We have our DAO component, which will be, take the pixel calibrator that writes calibrated images, that's read by the Python test script, and we check our result. So it means every block, independently of starting a whole system, can be numerically verified very quickly. We can also attach GUIs to these shared memories. So all the shared memories are interactable at every level. So your GUI just attaches to shared memories. It doesn't actually attach to any of the complicated numerical code. So from the GUI, you just write into shared memory if you want to close a loop. If you want to get your pixels on a display, you just read from the shared memory. Everything goes through shared memory. It's all available at all time. it's, yeah, I like this idea. So other powerful thing is in the shared header, we have timestamping ability. So every time we write the time it was written in that shared memory. So if you take the two shared memories, one from the camera controller, one from DM controller, you can get a rough estimate of your latency in real time of your system as it's running, without interacting with any of the actual numerical code. Okay, so the big question when we were developing this is, does this affect the performance of our system? Because we're writing and reading from these files, these shared files in memory. So I spent a long while testing this, and we have two methods to synchronize. The first method is use a series of semaphores that are handled by the kernel. The second method is we have a bunch of counters in that header, and those counters we can spin on. And in doing so, we can wake up quicker. We never hand the userland process over to the kernel, so we get no context switching or other things that could interrupt us. So on the far left is if we use this spinning on counters between two processes, we can wake up if we're located in cache regions in about 150 nanoseconds. And so if you're building real-time pipelines, you can easily make sure the header files are located where you want them. We can do it if you're just on the same socket, not using any cache, just on the same socket, we can do this in like 800 nanoseconds, or about separate sockets about 1 microsecond. On a simple system, you may go through 10 of these. Somewhere between 1 and 10 microseconds for loss in entire of latency just going through shared memory. It doesn't seem like a big penalty for the flexibility it gives us. And now for some applications it might be, and you want to reduce the number of times you jump through them, but we can do that. So the other ones, middle one is if we go through the standard semaphores. This involves going through the kernel and the semaphores. It's 6 to 15 microseconds. And the last one is if we just use our Python interface, about 50 microseconds. If you're doing it in Python, you probably don't care about the real-time performance, so 50 microseconds is fine. But yeah, it shows that the penalties aren't big in the grand scheme of things. We support multi-node architectures. So the top one, we have multiple cameras coming in. We process each camera on a different node. Then we recombine them on a single node at the back end that sends commands to either our mirror or multiple mirrors. So we can distribute calculations across computer nodes. So we support this. And we also support one camera going to multiple nodes and then recombine it. So big cameras, one big camera, many compute nodes. Both are supported. The other thing we spent a lot of time on is, so far I've been talking about writing and reading in shared memory, and it's mainly focused on like full frame applications. You get the whole image of your camera, you write it in shared memory. This has some benefits because it's simple, but we can also improve by writing partially. So every time you get a packet from the camera, we write that straight into shared memory. And we've got a bunch of ways to do that I won't go into because it gets a little complicated, but we can really hide all the latency of the full system. So this chronogram is from Harmony, scale mode, and we can really hide almost the entire computation behind the readout of the camera. We've really recently, we've started work on a Windows implementation. So one of the big things we found is a lot of hardware doesn't have drivers for Ubuntu, CentOS, no matter what we do on Linux. So we decided we really needed to support other systems. So we built everything we've done there on a Windows. We had to change some of it. So at first we started looking at MinGW to test it. We didn't really like that approach. So we went to the native Windows compiler, and yeah, we modified it. It took us actually a lot less time than we thought. It was about a day and a half. And now we're running on Windows. We've got a Meadowlark SLM running at, I think 1.5 kilohertz in the lab on Windows. Works brilliantly. So yeah, as I was saying, we can run on Linux, Windows, Mac. Not all of our tools work everywhere yet, but we're really working on expanding our support. And these shared memory regions, the big thing we're trying to do is we don't want to force languages on people who don't want to learn them or use them. So while we may write in C, C++ a lot of the time, I know a lot of people use Python, MATLAB, Julia is becoming more popular, and Rust I know is becoming more popular every day. So we have interfaces for all these, apart from Rust, which we are investigating, access all the data in shared memory in any of these languages at any time. So whatever tools you use now will be compatible. So another thing we're working on is right now to distribute between machines, you have to start processors on both machines and then set them up to talk to each other. We want to become a bit more automatic in doing that. So we're looking at accessing shared memory remotely. So like, let's say you turn up to a telescope and there's a shared memory server running on the RTC. You log on, you can see the server, you then request which shared memory you're interested in, and you subscribe to it remotely, and you can interact with it remotely without actually installing any DAO tools on your laptop. So yeah, it's using ZMQ, and with testing UDP and TDP, it's probably not going to work. This is not going to be designed for real time. This is designed for GUIs, telemetry-based systems, all your support infrastructure. But really just an easy way to turn up, put your laptop down, connect to the server and just start getting telemetry. So yeah, it allows for very heterogeneous compute environments. And we're currently in the testing phase of that now. So right now, DAO is in a private Git repo, mainly because our documentation is lacking. We're working on that. So hopefully we'll have a public release soon. If anyone wants access to it now, I can give you it. I have no problem doing that, just with the caveat. The documentation just isn't there. But one big thing for us to realize is, under UK law, deformable mirror control and the software that controls it is classified as dual use due to their worry about people building laser weapons with it. So if you want to use this for the DM controller only, none of the rest of, so the camera controllers are fine, the AO reconstructive tools are fine, just the deformable mirror control is certified as dual use. So we have to get you guys to sign an end user certificate to say, I promise not to make laser weapons with it. I'm sure you guys won't, but we have to get you to do that. Okay, so probably the more interesting bit. Now I've gone through all the tedium of what DAO is. This is going to be a very brief overview of many projects we're working with. So as I said, the first big ones are Harmony and Mosaic, the ELT instruments, and a few other listed there. We'll go through them very quickly, I think. So I think a lot of you guys know what Harmony is. I'm not going to go too much into detail of what Harmony actually is. But it's the first generation ELT instrument with interval field spectrograph. The interesting point is, well, it's changing. I don't know what I can really say about it at the moment. The big thing is, for the adaptive optic control system, we have, if I wish I had a pointer to show you. Anyway, what you need to know is there's a pyramid wavefront sensor, which will be for the main data path. There's also two other wavefront sensors, the Blue Shack, a Zelda. These are big cameras, but they are slow. Couple of 1 hertz, 10 hertz, nothing much for the, so they are done for the low order, slow low order, and the high contrast modes. Now, if they will actually exist when we come to finally build Harmony? No, I have no idea. But it runs about perfect. Cool. Okay, so it's been a while since I've looked at this. Anyway, so yeah, you got your pyramid wavefronts are here, and you got Blue Shack, which is, I think, an Allied Vision camera running at 1 hertz to control a low order DM. And then high contrast mode, we've got a Zelda wavefront sensor to update our reference slopes. And then we control all of the mirrors at about 500 hertz. I think a goal of 1 kilohertz. Now, this system is, I think that's all I really need to say about that right now. So Mosaic is a 2nd generation ELT instrument. So it's a multi-object spectrograph meant to be located next to Harmony. I don't think that's happening anymore. Anyway, so it's built on 3 legacy instruments. So Eagle, Optimus, and so with these ones, interesting note, when I did my PhD back in 2012, I was actually working on the RTC testing for Eagle. So it's all come full circle. I'm back working on Mosaic. Too many years later. Okay, so yeah, it's a very wide field multi-object spectrograph. So the field of view, I think, is across the whole image is about 7 arc minutes. It just does ground layer adaptive optics to feed many IFUs on a telecentric, non-telecentric focal plane. Now, don't ask me any questions about the A of science on this one. I'm only doing the RTC. So, yeah, okay. So timeline for this one. So this was meant to be a 2nd generation instrument. We are around here. PDR's scheduled for next year. So how does it look compared to Harmony? We have 4 LGS guide stars running the ESO LISA camera, and 4 NGS guide stars also running the LISA camera at 500 hertz. Cool. And so in Durham, we have a prototype test bed for this. So we have 2 sleds, each containing 4 servers of the dual epics. This one, I won't go too much detail. I don't think many people here care too much about CPU architectures or interested. Anyway, just to be aware, these were bought in 2019. They're 6 years old already. So any performance results are 6 years out of date already. Okay, so let's have a look at how we implement Harmony's pipeline in the lab. So this is running we're simulating an Occam 2K with a pyramid wavefront sensor. We split it between 3 nodes, HSC 1, 2, and 3, well, 2, 3, and 4. We do, all of them will do the full calibration, centroiding, and they will do parts of the MVM they're interested in. And each of them will send their part of the reconstructed wavefront to a combiner node, which combines them, does the filtering, adds in any disturbance data we need, and then sends it to our DMs. So for this, on 6-year-old hardware, we're getting about 250 microseconds and about 14 microseconds of jitter. Yeah, and this is from old hardware. So this is a scale system. 1 camera, basically 1 DM. Now, if we go to Mosaic's pipeline, this is a ground layer adaptive optic system with many LGS cameras and many NGS cameras. Just for the lab, we've only done 3 of them. It doesn't actually affect anything adding more. The combiner node will actually just add more in. So each server will do 1 camera. And so we've got 3 servers doing each of the cameras, combining at the back end. And if the one thing to notice is, even though these systems are pretty much as different as you can make them, when you look at the RTC layouts, they're almost identical. So we can reuse a lot of code. Now, we've just started working on this. We're too early really to say, but we're expecting the exact same latency. We're actually so confident we're actually not doing that much testing at the moment on it. We're too early in the process. So, quick summary of the ELT stuff. This all uses DAO. We're meeting our performances, and on the next slide you'll see we're tested the Harmony RTC on Sky. So Papyrus is a system that Lam have been developing for a number of years, and it's very Harmony-like. It's got a Occam 2K and a pyramid wavefront sensor, and runs at roughly the same frequencies as Harmony. We got slightly smaller DM, but it's very, very Harmony-like. So we asked them if we could use it as a risk mitigation platform for Harmony, and so we took our RTC and we put it on their system, and we've closed loop on Sky. So very quick, it's run at the OHP. It's a 1.5 meter telescope built in the 1960s. It's a very fun telescope. built so early, you have to do everything manually. It's a lot of fun working there. Anyway, here's a quick video of us closing the loop using Harmony's pipeline. Now, it's not perfect. We had to do a bit of hacking. So it's made by PhDs and postdocs. And one of the fun things was they had the philosophy of beg, borrow, and steal everything they could to make it work. So they borrowed one of a deformable mirror from Alpeo. That was one of their prototypes. So things are a little dodgy. It works great, but the interfaces are a little dodgy. So we actually had to use our Windows interface to, so we had to use a USB driver on the Windows machine to control it. So we had to take our commands out the back of our RTC, send them to a Windows machine running MATLAB and talk to it. So we got a bit of jitter there, but apart from that, it seems to work well. Yeah. So one cool thing about DAO is, as I said, it's very flexible. Last time we were up there, they gave me a new camera, the Sea Blue, and they wanted it integrated to do some optical gains tracking. So we just installed it, plugged it into the modes, did a gain optimization on the optical gains using PSF reconstruction, PSF of the Sea Blue, and just multiplied it against our modes. And yeah, this was very quick, and we implemented some optical gain tracking on the Sea Blue. So yeah, this is ongoing work that we're trying at the moment, which is great. So yeah, the OHP is actually being decommissioned next year. So Papyrus have been looking for a new home. So this is where the Icarus projects comes in. So in Asiago in Italy, they have a few telescopes, and one of them, the Sima Icar, is a 1.8 meter. And so they're going to house what was, I thought originally was going to be a new home for Papyrus, but it seems like it's going to be a new beginning. So, Durham, Lam, and INAF are all involved with building a whole new on-sky test bed for pyramid wavefront sensors in the CUDA focus of the Sima Icar. We had the kickoff meeting 2 weeks ago, and so not much is known about what we're actually going to do yet. We're just going to start seeing what we can do, but it's an on-sky test bed with visitor ports for visiting instruments. Yeah. Another system we're involved in is Matteo. Matteo is a MCO test bed run out of Padova. So it's there to test MCO concept. I forget exactly how big it is, but it has a lot of SLMs and DMs to create turbulence and correct MCO. It's potentially going to be used as a pathfinder for Morpheo that it wasn't originally designed to be. Procurement is starting, and we're going to begin putting the bench together next year. Okay, so the solar, we're also involved in some solar turbulence profiling at the DKIS telescope. So in the coming months, we're going to be putting a Shack-Hartmann based solar profiler on the DKIS telescope. This has a 5,000 by 4,000. I put a K there by mistake. It's not 4,000 K pixels. It's 4,000 pixels at about 400 hertz. This is over GigaVision. This equates to about 100 gigabytes of data per gigabits of data per second over GigaVision. So this is quite a numerically high demanding system. So we're using GPUs. So we do a cross correlation of the brightest pixel. We convert from slopes to covariance mapping, and then to go from covariance mapping to profiles, and potentially do wind profiling. So here's a couple of the GUIs we're using to analyze some of the sub apertures at the moment. Another thing, this isn't adaptive optic real-time control. This is MKIDs, so new detectors. So for those who don't know, I know you guys have them in the lab. I don't know how many you know much about them. They are microwave kinetic induction detectors. So when a photon hits some of these the detectors, which are at micro Kelvin, they break a Cooper pair, and we get change in the phase. So I'm going very quickly on this, but I don't really know the science behind the text. I just deal with the readout. So the resonators are measured at about 1 megahertz. And we get the photon energy and wavelength from integrating phase under these spikes. So we can use like match filters or something to detect them. And so we can, the great thing about that is we can detect different wavelengths on the same detector, and there is no noise, so we don't get any false positives, hopefully. Anyway, so we're looking at the readouts of this. So the way we're doing that, so we've got an MKIT array, we've got an FPGA doing the exciting the resonators with the RF, and then we're transmitting the phase directly to our servers. On our servers, we're using GPU direct to go straight from the network card to our GPU, where we're doing our match filters on the resonators. And so this work is just starting, where I think in the lab we've got 1 pixel that we're doing this path with. Hopefully soon we've got an array of 400 resonators. So that's work coming in, but this is a lot of data being transferred. And when we have arrays of actual big enough detectors to use as cameras in an AO systems, because this work is planned to be a pathfinder for PCS to see if we can use MKIDs as an actual detector, a wavefront detector for an AO system. But yeah, this has just started. We're just looking at just doing our initial tests. And then we're hopefully, once we get all our photon events from the GPU, we can actually plug these straight into an RTC and actually do real-time control on MKIDs directly. So, and most importantly, the EST. So we've been involved in the feasibility analysis up to now with the EST. What makes it interesting is large detectors, high frame rates, and very, very low latencies, which actually makes it a very interesting project. So while Harmony probably doesn't have an LTAO mode anymore, it's got 4 times the amount of data throughput as Harmony in LTAO mode and much lower latencies. So anyway, we've done a lot of feasibility analysis. We're starting to do some prototyping in our lab at the moment. And yeah, bring on PDR later this year. So just very quickly to conclude, DAO is a new RTC. It's not actually anything revolutionary. It's built on existing concepts. And our goal is to make it super easy to use for the user and allow the AO scientists to do AO science while being able to ignore the RTC. So it's easy to optimize, easy to implement. It's well suited for both labs and ELTs. And one of the big things is, because it's being supported by 2 ELT instruments, we're going to have at least 10 years plus of support. So it's got long-term support. Even if I left now, it's got too much inertia in these projects to be abandoned. So yeah, we'll improve directly with technology development, and we don't actually have a preference for CPU or GPU. We can be easily adapted to CPU or GPU, depends on the constraints of the project. But anyway, thank you all for listening. Any questions?
Okay. Thank you, David, for your presentation. It was very interesting, although I already know a few things of what you were saying. I have a question regarding the way of setting up the system. You're saying that the architecture, as it is split by shared memory, and you have blocks in between.
Yeah.
It's easy to improve the system or to try a different algorithm. But what about the configuration? How do you say to the blocks that goes behind and after that, which is the kind of output, the dimensions of the data, and all those kind of elements?
It's a really good question. So at the moment, we're trying to keep it as simple as possible for the user. So all of the processes will take in what they need from the command line. So you just pass it the handle of the shared memory. So that's the file name of the shared memory. And this will open the shared memory. So let's say let's take the pixel calibrator, because it's really very simple to understand. You pass it on the command line 4 pieces of information. Your raw pixel shared memory, your flat field, your background, or your dark, and your calibrated pixel shared memory. It will look at it'll open the first one, and it will be able to, from the metadata, retrieve how big it is. And from that, it will know how big to dimension itself. And so then it will open them all, check that they're all the same size, and then it knows how many pixels to calibrate because of the size of it. And we'll just work through all the pixels in there. So we're trying to keep it, each process will take in its configuration it needs on the command line, or you can pass YAML files to some of them. We're very open to everything. So we provide a lot of base tools that you can use, and most of them will take command line configuration. We can go more complicated, and if you have requirements, we can get much more creative with that. Like I know we were talking about having some Redis databases running with everything and it loads from there. We haven't implemented it because it's overkill. Most of the time in labs, you want to be starting things quickly, stopping them quickly. You don't want to mess around with, oh, where do I leave my YAML file? Where do I leave my configuration? You just want to start it up with these inputs, that output. So that's how it's done. We start all the processes in what we call we start all the processes in tmux sessions. Tmux is a way of running sessions in the background of your system so that you can just reopen that tmux session, and it'll open with that shell and where it was left of all the command line logging you've done, and you can just kill it by killing the tmux session. So you basically just launch your process in a tmux session and give it what inputs and what outputs. And now for one process, that's really, really simple and really easy. It gets a lot very complicated when you have 20 running with lots of different, but right now we don't want to implement, we don't want to force people to use how we think. Everyone thinks differently, everyone wants different tools. So we can provide some tools to start and stop. In fact, myself and Sylvain disagree quite a lot on how you should do a lot of this. And so we both implemented different ways to do it. But DAO is at the heart just a real-time message passing system, but via shared memory. Everything else is just a tool built on it. But yeah, everything's done on command line.
Thank you very much, David, for your talk. Could you elaborate a little bit more in the extra jitter that you have found when moving from Linux to Windows?
Okay, yeah. Sorry, I probably spoke quickly and didn't elaborate. So this isn't an issue with Windows causing jitter. I should have had a diagram here. Actually, if I go to here. So this is how it's the system's looking. So we've got our DM controller, and then this is a UDP stream to a Windows machine talking to DM. So this is where the machine's split. I maybe should have put a box here. This is a UDP stream to a Windows machine. This Windows machine has to run MATLAB to receive that data and talk to DM for historical reasons. We don't believe this is a Windows issue. We believe this is a MATLAB issue in this implementation. We did this very last minute because the Alpeo mirror we're using is very old and it's a prototype. So a lot of the electronics are prototype. And so it has a watchdog if you control it via the Ethernet controller, that every 2.5 seconds it will stop, do some cleanup, and before letting you control it again. It stops for 200 milliseconds. So you lose your loop every 200 milliseconds every like 2.5 seconds. So that wasn't viable. But using the USB on Windows, it doesn't seem to do that. And we don't know why. And Alpeo haven't told us why. We've asked them, but they haven't told us. So we decided this was the simplest way. And this was done at like 4 a.m. on an observing run. So, and I think everyone here knows that if you create a temporary solution, it's the permanent solution. So that's how that was created. And we believe it's coming from the MATLAB, not anything else. So, but we're in the process of buying some new electronics for it to get rid of that. But no, it's not an issue of Windows. Because we don't see it outside of this one instantiation we've got.
Okay, thank you. I have another one, if I may.
Yeah.
I wonder whether you have developed any simulation software, capable to generate, images in an easy way in order to test all the behavior. Something similar to the pair of dusk and dark that
Yep.
you had in the past.
Yeah, another great question. No, it's outside the remit of DAO. DAO is the real-time control system. There's much, much cleverer people than me doing simulation. So, like UPOW is the one that comes to my mind, built by Tycia over at Lam. He is far better at the simulations in AO Science than I ever will be. I don't plan to go down that route. I plan to use as much of his work as I can because it benefits him, it benefits us. So, no, in DAO itself, no, but we are, because of the simple interfaces, it's actually incredibly easy to pipe data in. So if I go back up to this slide for numerical testing. So we've got a Python script that pumps known data into a shared memory. We read it and then we put data out. If we just get rid of this Python test and we put an UPOW simulation there, it'll work. And UPOW Python, we've got the interface that works. We've shown it at Papyrus. We have a Papyrus twin in UPOW, and we can pump data directly from it into DAO and our results back into and close the loop in simulation. In fact, it works so well, they can run their simulations, calibrate the system using their simulation tool, give us their calibrated DM from their simulation tool, and use it on Sky directly. So no, it's a great question, but no, we don't want to go down that route. We are experts at this. There's experts at simulations outside it. We'd prefer to let them do their thing.
Okay, thank you very much.
David, thank you very much for your talk. Are you following any? You said that the telemetry can be read out from any platform. Are you following any standard? Because I know that in Europe is working in a specific standard for the telemetry in AO. Are you following it?
Yeah, so right now we are compatible with the real-time toolkit of ESO, so that is using MudPy. But I don't think that's the question you're asking. You were talking about this telemetry save format and fits that's being worked on. We haven't looked at it. We want to. That is a really thing that we want to do in the future. We haven't done it yet, but we do want to do it because I think saving telemetry in a standardized way is a really important feature. But that standard isn't a standard in terms of how you get telemetry from your system to a computer. That's how you save it as a file. And so we haven't implemented that because typically for me, that's slightly outside the remit of the RTC. That's the saving of telemetry. We can give you telemetry. Formatting at that side is actually pretty trivial, but yeah, maybe it's a tool we should bring in.
Another question. How hard would it be just to move from dark to DAO in a system working?
It's a great question. They are the different systems. It'd be starting a system from scratch. Now, I'm sure you have, I'll be right at the top. I'm sure you've got like a block diagram of what DAO's doing. Oh, Dark's doing. It's actually very, very simple for us to spin up identical components with shared memory in this way. Building the system, I actually think would probably take a week, couple of weeks. Testing it and verifying it, months, maybe if not more. Yeah, for me, it's not moving. They're not compatible in any way. You're building a whole new RTC from scratch. I wish I could tell you we have tools for it, but we don't.
Thank you.
Any question on the Zoom?
Okay, so I think that's if there is no any question. No more questions? Okay, so thank you, David, for coming and for giving this talk.